Hello, everybody, and welcome back to another video in Geography 340 Climatology. I am Dr. Zach Hilgendorf, and today we're going to be talking about dendrochronology. So here we're continuing our discussion on using proxy data sets to connect the dots and understand past climates. Dendrochronology, the study of tree rings and growth patterns, is where we're going to start out. What is dendrochronology? Well, it's basically dating and studying of annual rings in trees. Dendros, meaning from trees, or more specifically, the growth rings of trees. Chronos, time or past time, events in past time. Ology, the study of. So we can use that if we look at our little example tree here. To look at the pith, or the first year of growth. We can look at rainy seasons as, times where the tree rings are extra wide, dry seasons where they're condensed and much thinner. And then, for example, the scar from a forest fire scorching one side of the tree, acting as this black material on the edge. They're affected by things like temperature and rainfall. So tree growth is indicated by the size and color of the rings. They can hold information for no more than a few hundred years unless you're at a well-preserved archaeological site. But this can extend our record back a number of hundred to even more years in well-preserved examples. So we're going to start off talking about the principles of tree life cycles and dendrochronology using a series of animations created by the Arbor Day Foundation. I'll post some links below in case you want to check that out. But these are a phenomenal series of animations. So we're going to walk through and kind of understand what we're looking at with past climates for tree ring analysis. So here we're looking at an example of a 62-year-old tree over the next few slides. Again, all of these animations developed by the Arbor Day Foundation. Here, the outer bark is the tree's protection from the outside world. The inner bark, or phloem, is the pipeline through which food moves through the leaves to the rest of the tree. The cambium cell layer is the growing portion of the trunk, producing new bark and new wood each year. The sapwood, or xylem, is where water moves from the roots up to the leaves. And the heartwood is made of old xylem. It's the central supporting pillar of the tree. Each year, for the 62 years this example tree has been growing, it has added a new ring of xylem cells to the trunk. If a slice of the tree could be viewed, it would look like this. Each ring in this tree cross-section represents another year of growth. Every spring and summer, a tree adds a new layer of wood to its trunk. The wood formed in spring grows fast and is lighter because it consists of larger cells. In summer, growth is slower, forming smaller cells that produce darker wood. So when a tree is cut, the layer appears as alternating rings of light and dark wood. You can tell how old the tree is by counting the dark rings, one for each year. And these rings tell us a lot about what's happened to the tree over these years. So here we're marked off every 10 years by a white circle, but you can kind of see and count and infer what growth conditions were like as these trees were putting on each of its new rings. So how do you get this type of data? How do you sample and collect your samples? So we look here. This is an example from an actual tree. There's our pith, or the center portion of the tree. We see our early wood and our late wood. So that is recording the spring growth and summer growth and slowed growth. This is from a conifer tree. Early wood, the cells are thin walls with large diameters and they appear lighter in color. The late wood cells are thick walls with a small diameter and they appear darker in color. The rings from a porous angiosperm tree ring we can see here. Early wood, the vessels are much bigger than in late wood examples. But not all trees have rings. I don't have an example of it here, but if we take a second, we think, where would a tree not have a ring? Well, if we think about it, where would that tree not have variations in annual growth cycles? And if we think about that, where in the world doesn't have seasons? It's along the equator, right? So if we think of trees that are preferentially growing in equatorial regions where there are not considerable variations in solar insolation and day-night cycles, etc., that's where we're going to see trees that don't really have this type of tree ring distribution that we're looking at here. So the image below shows a conifer tree ring sample with about 30 rings. Every 10th ring is marked, going from left to right. The rings display a lot of variation, and you can see, see if I can grab my little pen here. Right here, we see this really thick layer. As we see it here, both of these here kind of extending out towards the edge of the tree. We see some really, really thick layers. Likewise, we see some really thin layers here and here, here, kind of continuing on out. Those are maybe years when precipitation or temperature weren't as hospitable to growth as they were when those larger tree rings were added on. So variation in these rings is due to variations in environmental conditions when they were formed. Cold or warm temperatures, dry or moist soil conditions, etc., even insect outbreaks and non-climatic factors like wildfires can impact how these rings are added on. Thus, studying this variation leads to improved understandings of past environmental conditions and is the basis for many research applications in dendrochronology. So how do we get these tree rings without killing the tree? Well, you can see here, that's what we call an increment borer. And we extract cores with that increment borer. You can see examples of what that looks like on these images kind of just above me here. This is what a boring tool looks like. So you put it against the tree and kind of spin it in, and it bores through the wood. And then you kind of turn. There's a portion on the very top, which we'll see here in just a second, and you kind of snap it, and it snaps the wood at the base, and you're able to extract that core out. Here you can see that core being extracted from the increment borer along this kind of sheath that sits within the borer as it's boring through the tree. If the tree is already dead or cut down, we can take a cross section from it and preserve this whole thing, which you can see here. Notice how wide the rings in the center are when this tree was young. It was growing much faster. Maybe conditions were more hospitable. It was able to get all of the nutrients and water it needed, but as it grew and put on more and required more energy and more nutrients, maybe its growth was slowed down a little bit. So how do we interpret these cores? Well, first we have to consider a few things, like site selection. Sites are selected based on criteria of tree ring sensitivity to an environmental variable, such as temperature, precipitation, etc. These would seem to be a bristlecone pine here, are some incredibly sought after trees because of how old they grow, how long they stay put, and the records that they can allow us to infer. Then you need to do things like this. We call this cross-dating or chronology building. What this is basically matching trees of unknown ages to those of known ages, looking at what those rings match and extending the record back. This allows us to assign exact dates to each tree ring. So we have a living tree that's been growing for a number of years, maybe back in the pre-1900s. We have a dead tree that overlaps, and we can see, if I was to circle this, we can see that those tree rings have a certain pattern that we can match up. And then say you have another older dead tree that we're able to say, oh, well, look at this. We have this pattern here that matches up well. So we're able to take the record that extends from the present day and extend it all the way back to the early 1800s. So let's think about that a little bit more. So let's say the sample was taken from a standing 4,000-year-old but very long dead bristlecone pine. Its outer growth rings were compared with the inner rings of a living tree. If the pattern of the individual ring widths in the two samples proved to be identical at some point, we can carry dating further into the past. With this method of matching overlapping patterns found in different wood samples, bristlecone chronologies have been established almost 9,000 years into the past because they might be in kind of low oxygen conditions, they decay slowly, they might be preserved under things like snow or ice along the sides of mountains. There are places where these trees exist that we can get at them and look at these incredibly old records. It's almost like a puzzle. You have to find the matching pieces, and if you can find the pieces that extend the chronology back far enough, you're looking thousands and thousands of years in the past. So this is a pretty extreme example, but we can look 9,000 years into the past to find what climatological conditions were when that bristlecone pine was growing. If we look here, this is kind of how we map these out. So these are ring width in millimeter versus time. So it's a time series analysis here. So we're looking at rapid growth when the tree was young, kind of smoothing out as the tree grows in age. Ring width indices with fast early growth trends are removed. So basically you're averaging this out to see an average index of growth. This is how we drive at those climatological records, by kind of removing the noise of that early growth signature to look at a more holistic and average growth over time. There are some challenges and limitations to that because this is not a perfect thing. Well, there are limiting factors. Growth can only occur as fast as allowed by the most limiting external stimuli. Too dry, the amount of rainfall is your limiting factor. Too cold or too hot, temperature is your limiting factor. Note, the limiting factor can vary from site to site, even in the same species of tree. So you can be across the ridge and maybe that saw more or less rainfall than on the other side of the ridge, depending on what type of climate you're in. So if you're on the north-facing slope versus a south-facing slope, your moisture and temperature are going to differ vastly. Missing rings and false rings can exist. So species limitations, some trees have no rings, non-annual rings, or poorly defined rings, and that's a problem. Trees must cross-date. If you can't develop a chronology or link to climate, then they're useless. You need a lot of times a master chronology or a master chronologist to be able to do this. And we want to get at a master chronology, looking at these tree rings as they extend as far back as possible to match up and corroborate the evidence we're seeing across species and across time. So two cross-dating challenges exist: missing rings or locally absent rings. So say you were taking a core and your increment borer went here. Uh-oh. Here's part of a ring that maybe wasn't fully developed, but if you were to go here, you'd add another year. So this is a missing ring or locally absent ring. So we look there. Here we count 4 years of growth. Not here. Here we only count 3 years of growth. So missing rings or locally absent rings are a concern or a problem. So you here would need multiple sources of evidence to be able to corroborate how many years this has been growing. False rings are another one. During stressful times, during growing seasons, trees begin to shut down and then growth resumes. So what you'll see is the full ring goes from here to here, but maybe a drought happened right here. So the tree was shutting down and we have this false band being added. So basically it looks like there were 2 years when there might have only been 1. That is where looking at multiple species in different regions and different climates can get at that difference. I'm going to post these again. North American drought reconstructions, causes and consequences. Tree ring reconstruction or reconstructed mega droughts over North America since 1300 AD. These are some awesome papers by David Stolley and others, and Edward Cook, to look at these paleoclimate reconstructions using dendrochronology. So give those a look. Just go ahead and Google them. I'll try to post them in the link below. These are some really valuable papers to look at if you want a better idea of how dendrochronology is used to extend our paleoclimate record. Here are some references that I used for this. In the next video, we're going to be talking about ice cores. This is a really cool one. Ice core dating methods are fascinating. So I will see you in the next video, and I hope you enjoyed this one. Have a great day. Thank you.